on this computer.
Looks like it's working.
Yes, we're recording.
Okay, great. So the outline of this talk, we're first going to do some background. We're going to talk about, the double affine Hecke algebra and how that gives us Macdonald polynomials, because that's precisely what we'll generalize to get SSV polynomials. Then I'll give you some background on alcove walks so I can introduce the combinatorial formula, generalizing something that Ram and Yip did back in 2010-ish. And then at the end, we'll go over some applications of this formula, and if there's time, connect it to Whittaker functions from metaplectic covers. So first, we have all the usual notation. In this talk, I'm just going to focus on the type A case. Everything could be done in other types, but SSV polynomials so far have only been defined in type A, so we'll just stick to that. And here I am going to do the GL case. So in particular, my weight lattice is going to be all the integer points. And yeah, so I'll have the usual standard basis, epsilon1 up to epsilon r, the usual finite roots, alpha I is the simple roots. Here, my Weyl group is going to be W0. And what I'm emphasizing here is the commutative presentation, because that is what I'll care about generalizing. And of course, type A, W0 is just the symmetric group. So you're all familiar with this, but any questions about the basic notation before I move on? Okay. And then, of course, we have affine versions of all of these things. So we can extend the Euclidean space with one more dimension. We'll call the corresponding basis vector delta, and the form is degenerate with respect to delta. We have the affine roots, which are finite roots plus some integer multiple of delta. Here, I only care about real roots because I want things you can reflect through. So when I say affine root, I mean real affine root. And similarly, we have the positive roots in the usual way. Positive finite root, or anything plus a positive number of deltas. We have alpha 0, the corresponding simple root. And the affine Weyl group satisfies the type A braid relations for this diagram, the circle diagram. One thing you might notice here is that the Weyl group I'm giving is technically the Weyl group you would associate with type SL, not GL. Right? I'm only having translations by the root lattice rather than the weight lattice. The reason I'm choosing to restrict my attention to this Weyl group is that this one is a commutative group, and it'll work nicely with the intertwiners I'll introduce later that give us recursions between SSV polynomials. Okay, so we have the usual actions of this Weyl group. We have the linear action on the extended space, which is given, as in cats or everywhere else. And the point is that the SIs, the S1 up to SR minus 1, are just going to act as permutations on the Euclidean space. And the translations are going to add or subtract some multiple of delta. And this is going to preserve the affine weight lattice. So it's going to preserve all the integer points. And of course, we have the corresponding affine action. So for that, we can view the extended space as functions on the Euclidean space using this form. So delta always acts by 1, and then the rest is the usual inner product. So I'm going quickly through this because I know you're all familiar with this stuff, but if there are any questions, please stop me. And, I seem to be lagging. There we are. So for each affine root, we can define the affine reflection. So this is a reflection on R to the R now. And under this action, still S1 to SR minus 1 are just permutations. And the translations are legitimate translations on this space. Mu acts on nu by nu plus mu. And I just wanted to write out explicitly what the action of S0 looks like here. What it's going to do is permute the first and last entries, and then add a 1 to the front, subtract a 1 from the end. So this is how the Weyl group will act on this space. And in particular, it preserves the weight lattice, the integer points. And what we'll need is the fundamental domain for this action. So if you use the action of the Weyl group, you can reduce any weight to something in this space. So it'll be a partition, a decreasing integer tuple, where the greatest difference is less than or equal to 1. So in particular, it's just some number of 1s followed by some number of 0s. Now, if I allowed myself to use the full Weyl group, the extended affine Weyl group, then I could just reduce everything to 0. But for reasons that will be clearer later, I don't want to do that. I'm just using W. And so this is my fundamental domain. Any questions? Okay. So now that we have the Weyl group and all of that squared away, we can talk about the double affine Hecke algebra. So this has generators T0 up to TR minus 1, which you should think of as sort of analogs of S0 to SR minus 1. And then it has powers of X to the mu hat.
Jason, I should say something, right? I mean, this action that you're describing, it's somehow mod Z, right? Because you're not changing the sum of the lambdas.
That's true. I'm not changing the sum of the lambdas.
So you can get to this plus maybe some constant vector or something.
Well, no. So if you notice, I didn't restrict that the lambdas are between 0 and 1. Oh, sorry. Yeah. So I shouldn't have written lambda in this form, right? Really, it's like C plus 1, and then C.
Bunch of C's. Yeah, that's all.
Right.
That's what I'm saying.
Okay. Yeah. Thanks for that correction. Is that okay? Okay. Right. So for the double affine Hecke algebra.
Yes.
So
yes.
Right. So for the double affine Hecke algebra, we have these T generators, and then we have X to the mu hat, where mu hat is in the affine weight lattice. And the relations here are first the type A braid relations, the same exact ones that we used for the affine Weyl group. Second, we have a quadratic relation generalizing SI squared equals 1. Here, TI squared is some multiple of TI plus some constant. We also have another generator omega and omega inverse, and omega commutes past the T's in this way. And the X's are a commutative subalgebra, and X to the mu, X to the lambda is X to the mu plus lambda. The reason we're doing this, the reason our double affine Hecke algebra includes the X's, is shortly we're going to introduce a representation of this on the space of polynomials. And this allows the polynomials themselves to sort of live in the algebra. And so the representation will come from the relations in the algebra. Really, this is just notation, but I allowed mu hat, the power of X, to live in the affine weight lattice. But X to the delta, I'm going to specialize to just be our parameter Q. So here we have two parameters floating around Q and K. And whenever X to the delta comes up, that's a Q. And finally, we have this cross relation between the T's and the X's. So this is sort of the most interesting part of this construction, because in the representation that I'm going to construct shortly, this is really where it comes from. What we're doing is we're taking what we want the representation to look like, and we're building it directly into the structure of the double affine Hecke algebra. That's essentially what Cherednik did when he constructed these, and that's how he got the Macdonald polynomials. But more on that later. Any questions on this before I continue? Okay. So analogously to these X's that we have, there's also a family of Y's. So we can define Y to the epsilon 1 up to Y epsilon R by the following formula. That expression is not so illuminating on its own. Really the point, well, first we can define Y mu hat for any mu by writing mu as a sum of epsilons and extending. And so these y's are commutative. So all of this is well defined and there's no trouble here. But the point of the y's is that they're sort of analogous to the x's. If we look at the cross relation between the t's and the y's, it's going to be nearly the same as what was satisfied by the x's, except this sign is slightly off. What's really happening is that the double affine Hecke algebra has some symmetry. There's an involution of this algebra that exchanges the x's and the y's, but the cost is that you have to invert the t's and also the parameters q and k. So if you take anything for the x's, you apply this involution, you'll get a similar thing for the y's, although some parts will get messed up like this sign. And so what we're going to do is we're going to define a representation of the double affine Hecke algebra on the space of Laurent polynomials in x1 to xr. And formally, that's the span of x to the mu, where mu is in the weight lattice. Here, I'm being vague about what my field F is. Really, F should be C adjoin Q and K, although later I'm going to enlarge this by adding in some other parameters. So the representation that Cherednik wrote down for the double affine Hecke algebra, we call it the basic representation, and it has the following formulas. So x to the mu just acts by itself. And omega also acts the same way it acted on the x's inside the double affine Hecke algebra. So really, we're sort of just taking the relations that were in the DAHA and we're imposing them on this representation. And similarly, this action of the TIs, if you compare it, even if you compare it to this Y formula, they're essentially the same thing, right? Essentially, this is coming from the relation between the T's and the X's in the algebra. Really, this is constructed from an induced representation. You have some action of the T's on the complex numbers, and then you induce to the whole double affine Hecke algebra, and the relations are going to give exactly these formulas you see here. Any questions? Okay. So the point of this, the reason why Cherednik constructed this double affine Hecke algebra is to get Macdonald polynomials. So if you look at these Y operators that I cooked up, one, I stated before that they're commutative, and two, under this representation, they're diagonalizable. The eigenfunctions, we're going to call them E mu, and they have this triangularity property. So E mu can be written as x to the mu plus lower terms with respect to some ordering that I'm not going to describe now, although I'll say a little bit more about it in the metaplectic case. And these polynomials are precisely the non-symmetric Macdonald polynomials. To recover the symmetric ones, there's a nice process to symmetrize. We won't need to go into that today. Okay. So part of what's nice about the non-symmetric Macdonald polynomials is that they actually satisfy a recursion. And this makes them so much easier to work with than the symmetric ones. So first, we can define the following intertwiners. So these tau i's are going to come up a lot for the rest of the talk. They're defined as some function in terms of the t's and the y's. Don't worry too much about this ti check. Really, this is the image of ti under some involution, the involution that exchanges the x's and the y's. But the technical formula isn't the point here. The point is this property that I've highlighted, that the intertwiners commute with the y's in such a way that they permute the power. The point of this is that they're going to let us take eigenfunctions, Macdonald polynomials, to other eigenfunctions. So if I take some, like, so if I let gamma of nu mu be the eigenvalue of y nu acting on e mu, then if I take tau I e mu, some intertwiner applied to a Macdonald polynomial, I can commute the y past it. I seem to be frozen. Oh, there we go. I can commute the y past it. I can apply the y to get the eigenvalue to come out. And then I apply a certain symmetry of these eigenvalues to see that what I got is exactly the eigenfunction with the eigenvalue for this guy. So what I just did is I applied the intertwiner and I got a new eigenfunction, which, because it has the appropriate eigenvalue, must be the corresponding Macdonald polynomial. So this allows me to take Macdonald polynomials to Macdonald polynomials. Any questions? I'm hearing something. Okay. So the point is, as I just said, that these tau i's take e mu to e si mu. And here, what I mean by this tilde notation is I just mean...
It may be that somebody has their mic on and they forgot. Usually, maybe you can mute people who are accidentally unmuted.
Can you click at the bottom where you have a little arrow? At the bottom of the slide.
That's okay. I'll continue. Oh, there it is. Okay. So right. So as I was saying, what I mean by this notation here is just that they are proportional by a non-zero scalar. So I got some eigenvector with the right eigenvalue. And if I scale appropriately, then it's going to be e mu. So this allows us, by using the intertwiners, to reduce a calculation of Macdonald polynomials to a calculation of E lambda, where lambda is in this fundamental domain that I wrote down earlier. And what's very helpful about this is that for any lambda in the fundamental domain, you can explicitly calculate what the y operators do to it, and you're going to get x to the lambda coming out. So this makes our calculation very nice. We can just put this in our computer. You start with x to the lambda, you apply the appropriate sequence of intertwiners, and there you go. There's your Macdonald polynomial. Up to some scalar, which if we care enough, we can explicitly track. Any questions? Okay. Just a side note. So one application of Macdonald polynomials is that they can be related to certain Iwahori-Whittaker functions coming from principal series representations. This will be more interesting to us in the SSV case, but the point of this is you compare the recursion that we just found with the recursion that arises naturally in that setting. And you see that the limit of this recursion will recover that one. And this was first observed by Brubaker, Bump, and Licata. Although it was Siddharth's student, Bogdan Ian, who told them to do it. But the nice thing about having such an explicit formula for these intertwiners and for the E lambda, where lambda is small, is that we can write down explicitly what's going to happen. And this is what Ram and Yip did around 2010. So they calculated E mu, where mu is in the root lattice. And here they did restrict themselves to the root lattice because they wanted every weight that they were looking at to be Weyl conjugate to 0. They didn't want to start from anything in the fundamental alcove, but specifically from E0. So they said, take mu, write it as some Weyl group element on 0, then take this W, give it a reduced expression, and expand it as a bunch of intertwiners. So this gives us explicitly a formula starting from 1, which is E0, to get to E mu. And this is essentially what I said above. But the interesting thing that they do is they take this product of intertwiners and they expand that in a pretty nice combinatorial way in terms of these objects called alcove walks. And I'll give more information on alcove walks later. But so they expand this product of intertwiners, they apply it to one, and they see what happens. And this gives them the alcove walk formula. That's what we're going to do in the SSV case, and then we'll observe that it can actually be pretty useful. A little observation is that we can generalize this formula to work for mu in the weight lattice. We just have to be okay with applying to x to the lambda rather than x to the 0. But that's fine. The formula is still very nice and gives nice consequences. I'm sure they knew this if they cared to do it. But if you're not looking at the SSV setting, it seems like a less natural thing to do. In the SSV setting, though, you can't get away with just extending the Weyl group. We genuinely need to enlarge the set of base cases for our recursion. More on that soon. So what I want to do now is I want to start stating the metaplectic versions of all of this stuff I've given you. And here I use the term metaplectic to just mean I'm putting an n into the notation and sort of stretching out the root lattice and weight lattice that I'm interested in. So we're going to fix some positive integer n. We now have the n affine weight lattice, which all I'm doing is I'm taking the finite part and putting an n on it. And I'm taking the affine part and actually putting an n squared. By affine part, I just mean the span of delta. And so that's what all of these formulas are doing. So alpha 0 n is now the same as alpha 0, but you put an n squared here and an n here. And alpha I n for I not 0 is just a multiple of alpha I. This partly is just a bookkeeping device, but what it's going to let us do is it's going to let us, one, define the n root system in the same way, and two, we can get this Weyl group Wn as a subgroup of the usual Weyl group. And what this is it's still the finite part, the finite Weyl group. And then instead of translations by anything in the root lattice, you can translate exactly by multiples of n in the root lattice. So like n times something in root lattice. And this n squared in these formulas is calculated so that that works out. So that under the actions we described above, this is exactly what you get. So the generators here are going to be S0n and then these SINs defined in this way. They're reflections in the new simple roots. And this W is really, this Wn, it's isomorphic to the original affine Weyl group W. We're not doing something new and profound here, but we'll see later that it is useful to have a separate name for it and to view it as a substructure of the big group. And if you write out this action and see what happens, S0n now is just a stretched version of what it was doing before. It permutes the first and last entries and adds a 1 to the front, adds an n to the front, subtracts an n from the end. So really, S0n is acting like a translation by n theta and a reflection in theta. So like I said before, this new Weyl group, it has the same Coxeter presentation as the other one. SIN goes to SI, they're isomorphic. This is primarily a device to help us think about these things in an easier way. Are there any questions about any of this before I move on?
Jason, should we think about these as n disjoint copies of everything, the Weyl group, the simple roots, and so on, or are they somehow intertwined with each other?
What do you mean by n disjoint copies?
Yeah.
Well, so it's not that I have oh, you mean like if I take like W1, W2 up to Wn?
Yes.
Oh, I see. Well, they definitely wouldn't be disjoint. Like if M divides N, then Wm contains Wn. So they're sort of nested as you increase N. The idea, I mean, the reason why these are interesting, and I'll talk more about it later, is that the SSV polynomials are going to satisfy another sort of triangularity like the Macdonald ones did. And the ordering there is going to come from the Bruhat order on this Wn group. And so it'll be interesting to us to understand how the Bruhat order on Wn interacts with the Bruhat order on like Wm, where M divides N.
Okay.
So that's why we're interested in all of these groups sort of nested in one another, rather than just saying it's isomorphic to W, let's move on. Okay. Does that sort of answer your question?
I'm just trying to get a geometric picture of the root system and the root lattice of for phi hat of n. How to visualize it.
Yeah, I mean, so the point really is that it's isomorphic to the original thing. So there's not anything that profound happening. We really just stretched it so that, like, if you like to think of the Weyl group via its action on the Euclidean space, we've really just stretched it so that the translations are now by multiples of n.
So,
sorry, if I may say something which may help. So if you think of the Weyl group, so you have a fundamental alcove for the affine Weyl group, right? There's a chamber.
Yep.
And the chamber has one affine wall.
Yes.
We made the affine wall bigger, I mean, further away. So the chamber became bigger.
So it's some sort of dilation.
Yeah, sort of well, I mean, there's an affine wall, which is, so there's the sort of walls passing through the origin, and there's one, for example, it's a triangle, let's say for SL3, you have a triangle, which is the fundamental alcove, and you have two simple roots that pass through zero, and another root, affine root, which is sitting, completing the triangle. Well, you just move that wall, you pick up much further away, so you go to n theta instead of theta. And so your fundamental chamber, your fundamental alcove is now a union of several old fundamental alcoves.
Oh, okay. So it's a union, but not a disjoint union.
No. I mean, it looks the same, right? I mean, you had these triangles, now you have much bigger triangles.
So you've got this sequence of dilations.
Yeah. You can keep moving this affine wall further away. And that's how these groups are sitting one inside the other.
Okay.
Does that help?
I love pictures.
Okay.
Yeah, so I'm going to have pictures of this sort of thing soon.
Okay.
So I'll show you, I'll point out what's happening. I'll show you what Siddhartha was just saying.
Okay.
By the way, this actually relates to the next line, which is if we look at the fundamental domain for the action of Wn on the weight lattice, then exactly as Siddhartha said, we enlarge the fundamental domain. Now we have still partitions, but the difference between the parts is now less than or equal to n. So we've essentially took, as he said, if we take, for example, this, and here was the fundamental alcove, we moved the wall out to here. So instead of this being 1, now we have n. So we have a larger fundamental alcove.
The new fundamental alcove has some tiling by old alcoves.
Right. Yeah, I mean, so the old alcoves fit inside of it, of course, like that. And so just as an example, if we look at like A5, if n is 5, then this fundamental domain for this action is significantly larger, right? For example, 520 is in here. So it's not so trivial as just a bunch of zeros and then some ones. There are a lot of elements of this fundamental domain, although they'll turn out to have easy SSV polynomials still. Okay, and in this setting, we also want to scale the double affine Hecke algebra. And this really is just for bookkeeping. It's going to be isomorphic to the usual double affine Hecke algebra. And so we'll keep the notation as similar as possible. So we have generators T0 up to TR minus 1. We have omega plus minus 1. And now we have X mu but now mu is in the n affine weight lattice, so it's in this thing. And all the relations are just like they were before, the braid relations, the quadratic relations. The only thing that's different is first, again, just bookkeeping really, x to the n squared delta is now q to the n. So we really only expect powers of x, multiples of delta to appear with an n squared in front of them. And so that's what's producing these q's. And the cross relations are equivalent to what we had before, except now we have to use sin here and alpha in. And this is just so that it matches what we had in the other case. The isomorphism between these, all you're doing is you're taking x to the mu and mapping it to x to the n mu and writing down what has to happen. So like I said, Hn is isomorphic to H. But what's interesting about this is that the basic representation, the thing that you get just by inducing, is now a representation on nth powers of x, right? Because that's what lives in the Hecke algebra now, is nth powers of x. And the thing that SSV did, Siddhartha and his collaborators, is they constructed a representation on all Laurent polynomials, not just nth powers. So I'll have to give a little bit more notation before I can state it. But as I just said, they extended this to representation on all Laurent polynomials. And what they were doing is they were trying to understand a Weyl group representation cooked up by Chinta and Gunnells. They were studying metaplectic covers of p-adic groups. And they had this Weyl group representation that they could prove using a computer it was a representation, but nobody understood where it came from. And what they did is they showed that it came from a particular Hecke algebra representation, which I will write down in a second. One more little bit of notation. So we had parameters q and k, but now we have some more parameters, gs, where s is an integer. And g0, we want that to be k. And we only care about the subscript modulo n. So if s is equivalent to t mod n, gs is gt. And if s is not equivalent to 0, then gs and g minus s are inverses. These really, they seem sort of unnatural. What happened is that in the setting where these first arose, there were certain Gauss sums that were showing up, and they happened to satisfy these properties. And what was observed is that these properties are actually all that mattered. So they instead just worked with abstract parameters satisfying these properties. And so then the result is that we can actually get a representation on the whole space of Laurent polynomials using the following formulas. So the x's act just like they did before. X mu acts by itself, except now mu is restricted to be an nth power. Omega acts by the exact same formula it did on the Hecke algebra. No change here. All that's different is the parts that I've highlighted. We have a g parameter showing up rather than a k first. Although if n is 1, or if nu is divisible by n, then this will go away and be a k again. And 2, in this exponent up here, we have this weird floor happening. And this sort of makes sense because what this is telling me is that this term is only going to affect the powers of x by multiples of n. So the second term permutes, and the first term only affects by multiples of n. But it's really not easy to see just by looking at this that this is a well-defined representation. Definitely not. So what they did instead is, similarly to the basic representation case, they constructed some induced representation and then took a quotient so that things worked out nicely. If you have questions about the details of this, thankfully Siddhartha is here to defend me.
Yeah, the floor had us completely floored when it showed up. I mean, it's right. So there's some integers, but now we have rational things, and taking the floor is some very nonlinear operation. And yet, that's sort of the magic, I think.
Mm-hmm.
Here, that you still get a well-defined representation of the Hecke algebra.
Right. Any questions on this before we keep going? Okay. And so in this setting, because the Hecke algebras are isomorphic, there are natural analogs of the Y operators and the intertwiners. I'm not going to write down the formulas again because they're basically the same thing. And the Y's still satisfy these nice cross relations with the T's, just like before, except now we have N's in the notation everywhere. So before I can write down the next thing, I need to give you a tiny bit more notation. So really the exact form of these does not matter, but I mean, it matters mathematically, but for this talk, it won't matter. What matters to us is that sigma is always going to be some power of k or maybe a g. And then this gamma is just a product of a bunch of sigmas. So in the end, it's going to be q to the something, k to the something, and then a bunch of g's. So this will make calculations easier later. And second, the real property that matters about these gammas is that if I have two nus, like nu and nu prime, I can tell them apart by using mu. And the only reason I care about this is that these are going to be eigenvalues of the Y operators. It turns out that the Y operators are again going to be diagonalizable. The eigenvalues will be exactly these gammas. And so this tells me I can tell which eigenfunction I'm looking at just by studying the eigenvalues, which again is exactly what happened in the Macdonald case. So let me state that more precisely. So the theorem of SSV is that there's a unique family of Laurent polynomials, E nu n, where nu is anything in the weight lattice, such that one, the Y's have the appropriate eigenvalue. And two, this is really just a normalization condition. The coefficient of x nu in E nu is 1. I mean, it's slightly more than the normalization condition because you need to know that there's a non-zero x nu coefficient. So you have to check that and then normalize it to be 1. And so this family of polynomials, these eigenfunctions of the Y's under this new representation, are precisely what we'll call the SSV polynomials. And nobody has called them this except me, because I'm the only one who's written something on them so far, but named after the authors. And so we'll write E mu n, sometimes in a way that emphasizes the dependence on all of these parameters. It makes it look more intimidating. And more importantly, sometimes I'll want to do things with these parameters, like specialize them to 0 or something. Any questions? Okay, so by the magic representation, we somehow have this new family of polynomials. But how do we actually understand what they are? How do we write them down? And the point is that we can use the same bag of tricks that we used in the Macdonald case. There's still a recursion. Oh, but before that, just to line up these SSV polynomials with what we already understand, if n is 1, everything reduces to what you're used to, and these are just Macdonald polynomials. But sort of cooler is that even for general n, if you only look at weights that are a multiple of n, if I take something like n times mu, then those will also be Macdonald polynomials. And you can just check this by looking at what the eigenvalues are. And they'll be Macdonald polynomials, except all the variables will be raised to the nth power. So take nth roots, and then you recover the Macdonald polynomials. So inside each family, the multiples of n give a copy of what you're used to, the Macdonald polynomials, and then there's all this smaller stuff. another nice example of an SSV polynomial, if lambda is in the fundamental domain of the Wn action, so if the greatest difference is less than or equal to n, and it's decreasing, then E lambda is just X lambda. So this is the best thing that could possibly happen to us. This is exactly what we wanted, that our base case in our recursion is going to be simple. And still, the taus, the analogs of the taus, satisfy this nice property with the y's. So we can show that we have a recursion just like in the Macdonald case. Tau I takes E mu to E Si mu, or Sin mu. So now, starting from the base case, starting from x to the lambda, I can apply some sequence of intertwiners, and I can get any Macdonald polynomial I want. Sorry, any SSV polynomial. Questions on this? Okay.
Yeah,
And
the
so this is,
intertwiners are somewhat funky because from time to time you have to take integer parts of things you're doing. So it's that's the whole subtlety, right? Because the T operators involve some integer parts.
right. So yeah, so when you're actually calculating the action of these intertwiners, it won't be as nice to calculate because exactly there's all these floors happening and things like that. But if we are just looking at the alcove walk formula, there all the work happens in the Hecke algebra, where the intertwiners are essentially the same intertwiners that we're used to. And then the funky part is just applying it to X lambda and seeing what happens. So that's what's really nice about this formula. So thanks for bringing that up.
Exactly.
So you really don't want to have to apply the intertwiners by hand. But okay, so this is going to lead to the alcove walk formula. But first I have to define alcove walks and give you some of the related terminology. So first, for each affine root, we're going to have H alpha hat, which is the hyperplane on which alpha hat vanishes. Remember that we're viewing alpha hat as a function on the Euclidean space. So the hyperplane is where it vanishes. And the alcoves are just the connected components of the Euclidean space minus these hyperplanes. So here we can have a picture, and this one I stole from Ram Yip's paper. So here we're looking at A2, so SL3, and we're projecting onto the span of alpha 1 and alpha 2. So here is alpha 1, here is alpha 2, and these little triangles are exactly the alcove. So I'm going to zoom in really quick so you can see the picture better. Probably a little disorienting. And so just to emphasize what Siddharth was saying before about the n extended Weyl group is that, like, let's say we were looking at W3, is that the alcoves would actually be like this instead. So this would be, oh, I went too far on that one. This would be the fundamental alcove. So that's what happens when we increase n, is our fundamental alcove gets bigger. But to keep things simple, I'm actually going to work only with alcove walks in the n equals 1 case, and then just translate them over to the general n case. But so these are what our alcoves look like. Let me zoom back out. And we've already sort of alluded to it, but I never officially wrote it down. The fundamental alcove is this thing that's labeled by 1 in this picture. And you can write it concretely as all the vectors that are strictly decreasing, where the differences are strictly less than 1. And as you can see in this picture, we can sort of correspond the alcoves with elements of the affine Weyl group by just identifying W with where W takes the fundamental alcove. And this follows because the action of W on the space is simply transitive. So you're not going to get multiple Weyl group elements taking it in the same place. We'll also want the closed fundamental alcove, which is just that same thing, but with weak inequalities. And that's what contains the fundamental domains from earlier, like A1. So now that we have alcoves, we can talk about alcove walks. What I want to do is I want to take some Weyl group element W, give it a reduced expression like this, and then I can study alcove walks of type W. So what they are is they're sequences of alcoves, or equivalently sequences of Weyl group elements that have the following form. So each step is either equal to the previous step, in which case we call that a fold, or it's similar to the previous step, but you multiply on the right by Sij, where Sij comes from this reduced expression. And written down algebraically like this, if you've never seen it, it probably makes no sense at all. So let me draw a picture. So what we're going to do is we're going to consider an alcove walk of type 0, 1, 2, starting at the fundamental alcove. So here's my picture. And if you see that blue path, what it does is it starts at the alcove 1, then it goes to S0, then it goes to S0, S1, and then it goes to S0, S1, S2. So we have this sequence of alcoves all adjacent to one another. And each one is either one step away from the next, or it's the same as the next. And so I call this unfolded because every step is different from the previous one. Or I don't call it that, Ram and Yip call it that, and I imitate them. Similarly, we can look at the orange path. So here we start at the fundamental alcove. So we're here, then we go to the S0 alcove, and then we choose to stay there. We choose not to pass through to S0, S1. And so we say we fold at that spot. There's a subtlety about negative versus positive folds that I'm not going to go into for the sake of time. And the pink path is another example that has two folds in it. We choose not to fold the first time, then we go to S1, then we choose not to fold the second time either. So you see the pink path sort of goes up to one wall, turns around, then goes through, turns around again, and stays like that.
So I guess the point is that you're in some alcove and you have walls all around you, and you choose a wall and you either go through it or not go through it. You toss a coin or something.
Exactly. And except we're only, oh, go ahead.
Yeah, and if the wall you go through or not go through, so there's one wall that maybe separates you from the fundamental alcove, and if that's the wall that you choose not to go through, then that's a negative fold.
Not necessarily. It depends on where you are positioned. I'm going to skip the negative thing because I'm looking at the clock and I'm running very short on time.
Okay, yeah, sure. Yeah, go ahead.
But yeah, I mean, but the idea of alcove. Oh,
yeah.
Go ahead.
No, that's fine. That's fine.
Okay.
I mean, right? It has to. Okay. Yeah.
Yeah, I can go into that during the questions. But so yeah, I'm going to skip the sign thing. So the idea behind alcove walks is that normally we would read S0, S1, S2 as being, reflect over alpha 2, then reflect over alpha 1, then reflect over alpha 0. But if you look at the sequence of alcoves that gives you, those aren't going to be consecutive. That's not an alcove walk like I was describing. So what you're going to do instead is you're going to take S0, S1, S2, and you're going to rewrite it. You move S1 to the right first. And then you move S0 past those. And because of this conjugation property that reflections have, you've now written it in terms of reflections through hyperplanes that are always going to be adjacent to your alcove. So in terms of a picture, what I mean is that given this decomposition here, S alpha 0 is now next to the fundamental alcove. You reflect. Now in the next step, you reflect not through alpha 1, but through where your first reflection took alpha 1. This orange hyperplane is where alpha 1 got taken by what you've already done. And so it's going to be next to your current alcove. And then similarly for the other steps. The way this is set up, the next step in your alcove walk is always going to be next to where you currently are. But okay, so the point is Ram and Yip used a principle similar to this with some subtleties about positive and negative folds to expand the intertwiner formula, the product of intertwiners. So let me just write down what that looks like in our setting, in the SSV setting. So there's a lot of notation here that I have not yet defined. What we're going to do is we're going to start with some mu, and then we're going to write it as mu equals some element of the n Weyl group times lambda, where lambda's in the fundamental domain in AN. And then given some reduced expression for this Wn, we can take that, the form of that reduced expression, and look at alcove walks of that shape. So this is going to be a sum over all alcove walks whose type is determined by this element Wn. And then we have some formula that looks kind of complicated, but hopefully in the last 5 or 10 minutes, I can convince you it's not so bad. So the first thing to know, if I scroll down a little bit, is that this power of x that appears here, this end n of p, what that is it's just the end point of the alcove walk, right? Your alcove walk, it's some path through alcoves and it ends somewhere. And that alcove is some Weyl group element. So what I'm doing, this end n, I'm just mapping that Weyl group element into the n Weyl group through the isomorphism. And those exactly determine the powers of x that are going to appear here. They're the endpoints of the Weyl group mapped into Wn applied to lambda. So this gives us control over what the powers of x look like. Other notation here. So these sigmas are the functions I defined earlier. They're just k or k inverse or maybe some g. So they might look a little ugly being there, but they're mostly harmless. And then these gammas are the eigenvalues of the y's on SSV polynomials. But what's very nice about this formula is that it reduces it to calculating those gammas only for lambda in the fundamental domain. So it's only in the very simplest case to calculate that I have to worry about what these coefficients are coming from the monomials. And there are these betas floating around and some etas. The betas, you can define them like this. What they really are is they're the walls crossed by an alcove walk of type W inverse. So if you sort of reverse the sort of alcove walks that we're considering, these will be the walls that they pass through. The exact form of this doesn't matter for our current discussion, but that's what's happening. So this looks sort of terrible. Let me try to convince you with some quick results why it's useful. But any questions before I do that? And is it okay if I go to 105? Because we always start late. Okay, I saw some nods, so I'm going to take that as a yes.
Yeah, I think that would be fine. Yeah.
Okay, thanks.
Of course.
Thank you. So, okay, so we have this scary looking formula. Let's see what we can do with it. The first corollary is a triangularity result, like what we had for Macdonald polynomials. There's some new partial order. This one depends on n, and really it comes from the Bruja order on Wn. And these E mu n's are triangular with respect to that partial order. So E mu is x to the mu plus lower terms. And this just comes from the analysis we were doing of what those powers of x are. So if I scroll up, I seem to be frozen again. Okay, if I scroll up, all of my powers, remember, it's the endpoint of some alcove walk applied to lambda. And if we write out what this, how I'm defining this Bruja order, which I haven't written down, these will be exactly the things that are less than mu. So it naturally gives us some sort of triangularity. But what's even cooler, and what I didn't realize till fairly recently, although it's easy to show, is that all of these coefficients, C nu, are non-zero. So this formula actually gives all of the powers that will show up and no extra ones. And to see that is actually pretty straightforward if you know what all the pieces involved are. If we look at this formula, right, it's possible that the same power of x appears multiple times. Different alcove walks could end at the same point. But if you specialize the parameters here, q and k, appropriately, you can make sure that every term in this sum has a strictly positive coefficient. And so then obviously there's no cancellation. So by looking at this alcove walk formula, we can directly see all of the powers of x that appear and no extra ones. Second, this follows immediately from the triangularity, is that this is a basis for the space of Laurent polynomials. You didn't need the alcove walk formula to prove this, but it's nice that it follows so immediately. Third, this is related to something I was discussing earlier, that if m divides n, then by comparing the Bruhat orders on Wm versus Wn, we can see that they're sort of nested. So the powers of x that appear in E mu n are contained in the powers of x appearing in E mu m. And therefore, those are contained in E mu 1, which is the Macdonald polynomial. So we sort of think of SSV polynomials as having fewer terms than the corresponding Macdonald polynomials. And it's not clear to me how you would actually prove this without the alcove walk formula, although it's when you calculate examples, you can sort of see it. I mean, actually, okay, you don't need the alcove walk formula. What you need is corollary 1. You need this triangularity, which you could prove without my formula. But so I guess the utility of the formula isn't necessarily these results, but how easy these results are. And hopefully how easy other results are. You can also do analogous things to get formulas for symmetrized SSV polynomials. In the Macdonald case, you have symmetric Macdonald polynomials. Here, there's a similar family, and they're not symmetric anymore. They're symmetric under this complicated Chinta-Gunnells Weyl group action, which is what motivated this whole project in the first place. And so you can get these Chinta-Gunnells symmetric things and get a nice alcove walk formula for them, which I won't terrify you by writing down. But it's just the other one, but slightly worse. And I'll stop in a second, but you can also consider Q limits of this alcove walk formula. It turns out that because of the form of this, because lambda is in the fundamental alcove and beta is defined the precise way it is, these always have strictly positive powers of Q. So when I take a limit, if I go back to this formula, right, if I let Q go to 0, then because these gammas have strictly positive powers, all the negative folds are 0. So any alcove walk that has a negative fold, it's gone. You only have positive folds. Similarly, if Q goes to infinity, then the positive fold terms go away. So what you get is that in the 0 limit, you have a sum over alcove walks that only allow positive folds. And in the infinity case, alcove walks only allow negative folds. And the coefficients get so much simpler. These sigmas don't go away, but then it's just k inverse minus k to some power. And what's nice about this, what allows us to then understand things like metaplectic Whittaker functions, which I won't have time to do today, is that if you're trying, like, let's say that in this case, mu is dominant. It turns out if you look at what's happening geometrically, if you have an alcove walk to something dominant and you try to fold, the first fold is going to be a negative fold. But no negative folds are allowed. So if mu is dominant, then E mu n is just x to the mu when you let Q go to 0. And similarly for the anti-dominant in the other case. So this allows us to understand the E mu's for like some fixed lambda, like just all of its permutations in the Q limits. You can understand them separately. And this is how you relate to Whittaker functions, which I will not discuss. I think I'll stop here. Thanks everyone for your attention.
there was a lot of stuff.
Yeah, I didn't realize I'd have to do such an acceleration at the end. I thought it would
Do
be
people
slightly
have
slower.
questions? I mean, it's very beautiful, and it's very this model that Jason has shows all sorts of properties of these polynomials, which I think so far people only know in this Whittaker limit. So that's the thing you didn't have a chance to talk about, but that's something that Henrik knows well, Henrik Gustafsson, and it's something that people working on multiple Dirichlet series have done. And these things show up as kind of local parts of some Euler product for automorphic forms on covers of adelic groups, which is why people were interested in them. But the formulas are really, really complicated. And so it's really great. I mean, one of the things that people are doing with Whittaker functions and so on is trying to understand vertex model formulas for them in terms of solvable vertex models. And here is something that's more general, and here is a formula for it. And I think this is kind of the beginning of something, and more cool stuff should come out of this. But these are very complicated things, so it's good to be able to tame them. Yeah, sorry. Please ask questions.
Just a trivial question. What's the infinity in the last formula?
Oh, so what I should have written is that's where the q goes. So it's the limit as q goes to infinity of e mu of x q k. So I'm taking that q parameter and sending it to infinity, or in the other formula 0.
So you've got some, so it approaches some finite object?
Yeah. So the dependence on q is sort of balanced out. Like if I go back to the formula above, the only dependence on q in this formula is in these gammas. And it always appears to a positive power.
Mm-hmm.
So if q goes to infinity, then these ones are just going to cancel each other out because they're the same. So you're going to get a minus times this coefficient here. And these ones would just go to 0. So the q goes to infinity limit is perfectly well defined.
That's amazing.
Thanks.
Yeah, so I mean, I should say one thing. I mean, especially because Jason didn't have a chance to say it, that when, let's say, you put q equals 0 or infinity, then there is a surviving k, one parameter.
Oh, okay.
Okay, and what this thing is supposed to be catching is some formula for the, I guess, the p part of some Euler product. And the k is essentially the p, or the size of the residue class field or something.
Mm-hmm.
And that's where all the Gauss sums and so on were coming in. I mean, it's all combinatorics, but it's combinatorics in service of some number theoretic thing, which is completely natural. I mean, these complicated formulas cannot kind of exist without any reason.
Right.
So there is a reason. And the whole point of all of this theory is that you can do a one parameter deformation of the theory,
Mm-hmm.
which is kind of not obvious from the number theory point of view, or even from the vertex model point of view. So this q, which you can put equal to 0 or infinity, is the new thing in all of this.
Mm.
So what vertex models might be related in
Maybe
mechanics?
Henrik can. So it's. I mean, Henrik can talk about that because he does that quite a bit. But it's it's these 6 vertex models. So it's not. I don't know. I mean, there's some connection to VOA, right? But
Not directly. But what about the hard hexagon model?
Henrik, maybe
because-
you can say
Just a random question, because that happens to be related to the
hard hexagon.
to the Rogers-Ramanujan identities.
Yeah, I don't know about the hard hexagon in
Just
particular.
curious.
Yeah, do you have any input, Henrik?
No,
But-
not about the hard hexagon. No,
Just
it's
curious.
it's a 6-vertex model which involves both adding colors and another attribute we call scalar to lines forming in this model. But I don't know about the other one you mentioned, I'm afraid.
But these are ice type models, right?
Yes, that's right.
The 6-vertex model is this ice type model.
Yes,
or
we call it metaplectic ice.
Metaplectic ice, yes. Okay, but before it became metaplectic, it was ice
Yes, yes.
or easing or something.
Not easing, but
Not easing.
some ice model. Yes.
Ice model. So the Q equals 0 limit is some grown-up version of the ice model with colors and supercolors.
Right. Yeah, I have to be careful because we're using Q for your K and
Yeah, but that's okay.
so-
It's one.
Right.
Right. Never mind. It's a one parameter versus two parameter.
Yes.
There is one parameter story which has all of these nice ice type models, which Dan Bump and Henrik and Ben Brubaker
And Valentin Bukimas.
Valentin Bukimas and have been working on. And this is some version of the story with an extra parameter. I mean, just as Macdonald polynomials somehow shouldn't exist, what Macdonald did was he took his famous formula for spherical functions for p-adic groups, and he added a parameter to that. So Macdonald has the famous formula for spherical functions for p-adic groups, and he just essentially that they were somehow Hall-Littlewood polynomials, and he added a parameter to that. Then Whittaker functions are somehow generalizations of spherical functions. You use an Ewahori subgroup rather than the maximal compact. And then you can do a metaplectic story. So you can look at some cover of the p-adic group and which splits on the maximal compact. And you can define all of these things. So you can have an n-fold cover. And you still have those Ewahori-Whittaker type functions, and those happen to be somehow the Q goes to 0 limit here.
So going from the spherical Whittaker to the Ewahori-Whittaker is where you introduce the color. And when you
Yes.
introduce the metaplectic cover, you introduce the other attribute.
The
we call
supercolors.
Supercolors, yeah.
Yes.
Jason, could I ask you, could you remind me where the parameters, the G parameters ended up in the formula? What happened to them?
So in the Q limit, all of the G parameters are hidden inside these sigma coefficients. So the sigma is going to be K inverse in certain situations, K in others, or G of S. in others.
Right, thank you.
Sure.
So
Okay, so
the Gauss sums are all sitting inside sigma.
Right. And so, yeah, something I'd like to know, but I haven't looked into, is whether this formula tells us anything interesting about Whittaker functions. Like, is this something that is already known, or what?
Whether it can be deduced from the ice models.
Yeah, or that.
Yeah, I would have to think about it and ask my collaborators if they are familiar, but I'm not familiar with.
And yeah, I'm
So
going to give.
I think Jason has been invited to give a talk at this.
Oh, great.
Yeah,
we
so I'm
have-
talking
Stanford
about
MIT
this on
seminar.
Wednesday at that seminar. So you'll see it again, Henrik. And
Great.
I'll try to pitch it more toward that group. I'll maybe cut some things out so I can talk about Whittaker functions.
Yeah. I mean, it might be worthwhile, Jason. We can talk a little bit about it, but might be worthwhile to start from the end.
Could be. Yeah, let's discuss when we meet later.
Okay.
Thanks for the great talk, Jason.
Yeah. Thanks for coming and for letting me speak here.
Pleasure.
It's very nice work. I mean, it's just so nice.
I have to get going. See you.
Bye.
Right.
Bye, everyone.
Bye. Thanks again.
Bye.
So